Hello friends. So, we were discussing about the rectangular family of elements, and we discussed about how the interpolation functions, they have to satisfy the partition of unity concept to be able to represent the rigid body modes. So, sum of that is essential, and this requirement is holds equally well for the triangular elements as well. So, all the finite elements for solid mechanics that are used for solid mechanics problems, they need to satisfy, and also for other constant value of primary variable. If that requirement is to be included in the approximation, then it is essential that the interpolation functions have to satisfy, they have to add up to unity at every point. So, this has to be satisfied uniformly at all points of within the domain, within the element. So, at all points of x y, all possibilities of x y within the element domain, these interpolation functions, they should add up to unity, right. And this is obviously true at the nodes, because at nodes only one of them will be unity, all other interpolation functions will vanish at node. For example, at node 1, n 1 is equal to unity, n 2, n 3, n 4, they will all be 0 at node 1. At node 2, n 2 will be unity, but n 1, n 3 and n 4, they will all vanish at node 2, and similarly for node 3 and 4. But this requirement is not just to be satisfied at the nodes, but at every point in the domain, in the interior of the domain, and that is crucial, because this interpolation condition is easy to satisfy, that is n I x j y j is equal to delta I j. So, this is not that difficult to satisfy. So, interpolation condition can be derived, and it can be managed in several ways, but we need to look at that set of interpolation functions, which will, in addition to satisfying this interpolation condition, they also satisfy the requirement of those being partition of unity, those divide the unity amongst themselves, right. So, now we go to the next point of discussion, the particular ways in which Lagrange interpolation and the serendipity interpolation functions are derived. So, Lagrange interpolation and Lagrange family is simply defined as, if I have the coordinate frame so there can be grid lines for constant value of x and y, and I define the nodes at these grid points. So, for example, for a 4 noded triangle, 4 noded rectangle, we defined the intersection between these 4 grid lines, right. So, this is equal to x is equal to 1, let us say this is equal to x is equal to 2, this is x is equal to minus 1, x is equal to minus 2, and similarly there will be y is equal to 2, y is equal to 1, y is equal to minus 1, y is equal to minus 2. So, these are the grid lines. So, 4 noded rectangle is defined by these 4, any 4 points which are defined by the grid lines, not necessarily x is equal to 1 and y is equal to 1 and so on. They can be any 4 points which are located at the grid points of the coordinate system, Cartesian coordinate system, or coordinate system more precisely. So, higher order term, I mean these 4 points, they define the rectangular geometry. So, if I need to have, this is the minimum I need to define variation of primary variable that is complete up to first degree. So, that it contains the constant term which will model the rigid body motion, and it also contains the linear terms which will model the constant strain conditions. But if I wish to, and the error in approximation is of the order of second degree polynomial, approximation of displacements is second degree. Although the second degree term is present in the approximation in the form of x and y product x y term, cross product term, but the second degree other two terms of the second degree polynomial x square and y square, they are not included in the approximation. So, they do not contribute to the general quadratic variation. So, this element 4 noded element is not capable of representing complete quadratic. So, I can define higher order elements by, let us say, quadratic term. If I need to include 4 quadratic, I mean the polynomial approximation of primary variable up to complete quadratic. So, up to complete quadratic, that means I need to have 2 terms in each. So, second degree in x and second degree in y. So, what is done is for the interpolation function, so n I x y is equal to L I x multiplied by L I y. So, where L I x is equal to x minus x j divided by x I minus x j, and this is j is equal to 1, 2, 3 and I is not equal to j. So, p plus 1. So, this is pth degree. So, Lagrange's interpolation of pth degree, complete pth degree, will have these terms ranging from 1 to p plus 1 and one term less when I is not equal to j, right. So, that it becomes, for example, for second degree polynomial it will have 2 terms, right, and that is what it will have. And similarly, for L I for y pth degree polynomial, this is product j is equal to 1, p plus 1, I not equal to j, y minus y j divided by y I minus y j. So, these are the 2 terms, and if you look at the previous derivation, this is all first degree Lagrangian interpolation in x multiplied by first degree Lagrangian interpolation in y, right. So, this should be actually up to p plus 1, yeah. Only then there will be by removing one term for which I is not equal to j, there will be p number of terms in this product. So, this is first degree polynomial in x multiplied by first degree polynomial in y, and together they give us the required terms. And what are the terms here? It would be instructive. So, there is a term x multiplied by y, so that is cross term, then 1 multiplied by x then 1 multiplied by y, and then 1 multiplied by 1. So, those are the terms in the Pascal triangle. So, 1 multiplied by 1, that is the constant term, x multiplied by 1. So, that is called linear term, y multiplied by 1, that is linear term, and then x multiplied by y, that becomes x y term. And similarly, if I multiply by the quadratic terms, quadratic interpolation model. So, I will have, for example, I need to take the elements, what are the elements that will be required, right. So, what are the elements that will be required? So, we will need to have 3 nodes in each side. So, I can have these possible nodes, and this becomes the interpolation. This becomes the element, right. So, there can be actually sorry it is possible to have interpolation So, this is the node, this is the element that we will have omega e, nodes being 1, 2, 3, 4, 5, 6, 7, 8 and 9. So, a total of 9 nodes. So, as you can see, the nodes are all placed along the intersection of the grid lines, constant values of coordinate lines, and each of these constant values of coordinate lines are defined by one of these equations. These are called the zeros of those lines or the equations of those lines, x minus x j is equal to 0 or y minus y j is equal to 0. So, we just multiply by the zeros and then normalize the numerator, evaluate the numerator at the corresponding node, substitute the values of the coordinates of the corresponding node, and then divide the numerator by this value. So, that it becomes normalized to unit value. So, this way we can have, in this case, the for interpolation function for node 1, we can have y minus y 1. So, that is in this case it is simply, or this is only x is equal to 0, because y axis is oriented along this. So, this is x is equal to 0 line, and this is x 1 minus x is equal to 0 line, and this is 1 plus x is equal to 0 line, and this one is y is equal to 0, and this one is 1 minus y is equal to 0, and this is 2 minus y is equal to 0. So, that is the equation of those lines, and that is what we need to substitute here. So, these are what those lines are, y minus y j, y minus y j, and product evaluated at ith node, divide by that, and that becomes normalized. So, in this particular case it will have, so L 1 is equal to, I will need to multiply x of 5, L 1 is equal to x minus 0. So, to say this is the coordinate 0 and multiplied by x minus 1 divided by, this is minus 1 multiplied by minus 1 minus 1. So, this numerator evaluated at x is equal to 1 at the node 1. So, at node 1 it is x value is, x coordinate is minus 1. So, that is what it becomes here. So, this becomes half x x minus 1. And similarly for L 2, so this is quadratic and second degree polynomial for y in terms of y for node 1 will require this equation and this equation. So, 1 minus y minus 1 multiplied by y minus 2 and then the value of the y coordinate of node 1 is 0. So, it becomes 0 minus 1 multiplied by 0 minus 2. So, that is equal to again 1 over 2 y minus 1 y minus 2. So, this is what it is, and the product the n 1 then becomes 1 by 4 x square minus x. I multiplied these two together multiplied by y square minus 3 y plus 2. So, I take the product of these two terms and then these two terms they need to be multiplied. So, what are the product, what are the terms that we are looking at? So, there will be a constant term in general. So, there would be some approximation, I will just say 1 by 4 x square y square, then there will be x y square and then minus 3 x square y plus 3 x y plus 2 x square minus 2 x. So, these are the terms in shape function for node 1, and similarly there would be other terms coming from the shape functions of node 2, node 3, node 4, node 5, node 6, node 7, node 8 and node 9. So, in general there will be 9 terms in the approximation. Total polynomial approximation will have 9 terms, and what are those 9 terms going to be? So, let us calculate again going from the Pascal triangle. So, 1, so up to this 1, 2, 3, 4, 5, 6. So, these are all there. Then beyond this we need 3 more terms to complete the total of 9, because there are 9 nodes that come on the grid lines. So, these grid lines they intersect total at 9 points. So, there have to be 9 nodes in the approximation, and that will require 9 number of polynomial terms. So, what would be those 9 polynomial terms? So, up to this quadratic complete it is 6 terms, right. So, these are 6 terms. In addition to these 6 terms, we need to include 3 more terms, and those 3 more terms obviously have to be located symmetrically in the Pascal triangle to maintain geometric isotropy. So, those 3 terms would be x square y, x y square and x square y square. So, these 3 terms they are spurious terms. They do not contribute to the convergence requirement, rather they pollute the approximation. The approximation is only complete up to second degree polynomial. So, these higher degree polynomial terms they are only placeholders just to ensure unique approximation, unique solution. So, that we have one to one mapping between the number of nodes and the terms of the polynomial, right. So, these are the 3 interpolation polynomials, and as we see for 4 noded rectangle we had one spurious term, that is extra term beyond the required or intended degree of completeness. In case of quadratic completeness target, when we target to have complete quadratic variation, then we have 3 spurious terms, 3 extra terms from higher order. Now, they are also not of the same degree. So, there are 2 from the cubic variation and 1 from the quartic variation, 4th degree variation. And similarly, if we try to go further up for the cubic complete variation, there would be still much further number of much larger number of spurious terms in the polynomial approximation that need to be included. And that large number of higher degree polynomials, that is actually not good for the quality of approximation. We have seen this in our interpolation while our discussion of interpolation approximation in approximation of Runge's function. Higher degree polynomial terms, they lead to very wild oscillations between the nodes of interpolation. So, these higher degree interpolation terms which are not contributing to the convergence requirement or the accuracy of the finite element solution, they are they should be minimized, because they are trying to they will corrupt the polynomial approximation, quality of approximation. And it is for this reason that serendipity elements were developed to cut down on these extra terms that figure in the Lagrange interpolation. So, Lagrange interpolation model is very easy to develop. It is just product of Lagrangian interpolation in x direction, multiply it with the desired Lagrangian interpolation in y direction, and that is all. And for the 3 dimensions, it would be another Lagrangian interpolation in z direction, and all is well. So, complete interpolation model is defined, but that would involve a lot number of spurious higher order terms, which are not really contributing to the problem, contributing to the accuracy of the solution. And further, they also, another issue is they also require more number of nodes, and more number of nodes, that means it increases the problem size, because those primary variables are part of the solution. And in this case, there is one internal node here, interior node here, 9th node. So, for quadratic approximation, there is one interior node, and this interior node does not contribute anything towards the inter element compatibility, inter element continuity. So, inter element continuity of the solution approximation, which will ensure piecewise continuous variation of the approximation from one element to the next element. So, this interior node does not contribute at all, and these number of interior nodes will keep on increasing more and more. For second degree complete, we have one interior node. If we go for third degree complete approximation, we will have 4 interior nodes. There will be total of 16 terms, 16 nodes, right, 4 on each side, and then 4 in the interior node. So, there will be problem. So, that not only increases the problem size, and it also adds extraneous higher order terms, which will distort the approximation, polynomial approximation. And with this objective to cut down on the, to eliminate these interior nodes from the approximation, and at the same time that will also have the added benefit of reducing the number of spurious terms, the serendipity elements were developed. And those serendipity elements are developed in a very straightforward logical way, I would say, if not straightforward. So, what are those techniques? Let us discuss by using an example. So, for serendipity element, the quadratic complete first element is same in Lagrangian and serendipity element 4 noded rectangle So, that is the simplest rectangular geometry we can have. So, there is no difference between the serendipity element and the Lagrangian element as far as 4 noded rectangle is concerned. But for second degree complete, we aim for an element of this type. The problem was an interior node in the Lagrangian element. So, this ninth node that was in the interior of the domain in case of Lagrangian interpolation, we will eliminate that, because the inter element continuity is defined only by the nodes on the edges of the element. So, let us number these nodes 1, 2, 3, 4, 4 corner nodes, and then the mid side nodes 5, 6, 7, 8. Now, again the equations would be given by x is equal to, let us say 1, and this is x is equal to minus 1, and this is x is equal to 0, and similarly this one is y is equal to minus 1, y is equal to 0, and y is equal to plus 1. So, what is done here is it is easier to visualize the interpolation functions for mid side nodes 5, 6, 7 and 8, in the sense that these interpolation functions, they have to be 0 on, let us say n 5, n 5 has to vanish on these 3 lines, and then it has to take unit value at node 5, right. So, n 5 has to vanish along this line and this line. So, a very simple way to do that is multiply the zeros of this line and this line, and that is in some way proportional to the interpolation function for node 5, and then I evaluate it at the coordinates of the node 5 and normalize it to unit length, unit value. So, that way it becomes very simple. Let me just say n 5 x y is simply given by 1 minus x and 1 plus x, and this is 1 minus y, right, and then I divide it. What are the coordinates of node 5? Y is equal to 0, no, y is equal to minus 1 and x is equal to 0. So, this is 1 minus 0, 1 plus 0, and y is equal to 1 minus of minus 1. So, this is simply 1 minus x square 1 minus y divided by 2. So, this is n 5 interpolation function for node 5, and if we look at the variation, its variation looks like it will have quadratic variation and then so this is 1 and it vanishes to 0 at the edge 1 and 4 and 2 and 3 and 3 4. So, this is node 5. So, this is n 5, n 5 has quadratic variation and then linear variation in with respect to y. So, it linearly vanishes to 0 at the other with respect to y, but with respect to x it has a quadratic variation. Similarly, for n 6 I can write, or it would be instructive to or more useful to take n 7 or n 8, right, 5 and 8, because that will help us in defining the interpolation function for node 1. So, for n 8 interpolation function for node 8, I can multiply the equation of line 3 4 and equation of line 1 2 and equation of line 2 3. So, that would ensure that n 8 satisfies the interpolation condition of vanishing on all other nodes except node 8. So, that would be 1 minus y, 1 plus y, and this is 1 minus x, and that has to be substituted for node 8 coordinates. So, coordinate of node 8 is y is equal to 0 and x is equal to minus 1. So, 1 minus 0, 1 plus 0 and 1 minus of minus 1. So, again that is equal to 1 minus y square, 1 minus x by 2. So, it will be similar kind of quadratic variation along y and then it linearly vanishing to 0 at with respect to x along edge 2 3. And similarly, we can define the interpolation functions for 6 and 7 by suitable product of zeros of the 3 lines. Now, what is done is we can define n 1 x y, the interpolation function for node 1 is x minus 1 y minus 1 by 4 for the 4 noded rectangle. So, we make use of that. So, n x y is equal to one minus x and 1 minus y by 4. So, when what is this function? 1 minus x 1 minus y will have variation of 1 at node 1 and it will linearly vary to 0 at nodes 2 and 3, right, and this will have, because node 5 is at midpoint. So, this will have a value of half at node 5 and similarly this will have a value of, I mean this bilinear interpolation for 4 node rectangle, this will have a value of half at node 8. So, what I need to do is I can pull this down so as to have 0 value at node 5 and node 8 suitably. Now, how can I do that? I know that n 5 evaluates to unity at node 5 and it has no effect on other nodes, right. At all other nodes n 5 is 0. So, all that I need to do is subtract half of n 5. So, this will reduce, this will pull down this bilinear by half at node 5 and it will not have any effect on rest of the nodes. And similarly, I can pull down this at node 8. So, that this interpolation function for node 1 is given by bilinear variation that was derived for 4 noded rectangle and then modifications, local modifications by the mid side nodes, appropriate mid side nodes. So, for n 5 and n 8. Similarly, for n 2 it can be derived from bilinear shape function for 4 node rectangle and then suitable corrections incorporated for node 5 and node 6. For node 3 it will be similarly done by using suitable corrections for node 6 and node 7, and for node 4 it will involve corrections for node 7 and node 8, and that way we will have the complete interpolation functions, and we will see if we try to examine it will, we will find that they all satisfy the partition of unity concept as well as satisfying the basic requirement of the interpolation criteria, that is n I evaluated at x j y j should be equal to delta I j, the Kronecker delta. So, we can derive this for higher order terms, and for third degree complete we will have only fewer number of elements, and for quadratic element, as we can see, there are 8 number of nodes. So, there will be 8 terms in the polynomial, and that would involve only these 2 terms. So, this extra term that was there in the Lagrangian interpolation, that is eliminated, that is not required. So, we can cut down on the higher degree polynomial, higher degree terms, and similarly we will have 12 node rectangle for the cubic variation. So, I can have at 1/3 points so total 12 number of nodes. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Total 12 number of nodes, and together with this 12 number of nodes we can derive the interpolation functions for which are complete up to third degree polynomial. Contrast these with the Lagrangian interpolation, which would require nodes at these 4 points as well, 4 interior nodes, and those 4 interior nodes would require 4 extra terms in the polynomial. And for 12 node interpolation there would be this would involve 6 plus 4. So, these are 10 terms, and from 10 terms we will only require 1 extra term here, 1 extra term here. So, only 2 extra terms, higher order terms in case of serendipity element, but for the Lagrangian element there would be much more, I mean there would be 4 extra terms. So, there it will involve all these 3 terms and then 1 extra term here. So, that would be x cube y cube term. So, total of 4 extra terms. In the polynomial approximation, and that is a major problem. But increasingly as we go above higher order interpolation, it becomes increasingly more and more difficult to find appropriate interpolation functions for serendipity elements. Fortunately, we do not require to go for very higher order interpolation. We generally do not go beyond quadratic. Cubic is about the maximum that we need for finite element approximation, and for that purpose serendipity elements are a very good choice. But certain application areas, the Lagrangian interpolation is also useful, and particularly for lower order, for example quadratic element, there is not much to choose between Lagrangian and serendipity. It is only a matter of 1 extra node, not much of a difference, but for cubic element of course serendipity element and Lagrangian element, they make a lot of difference in the number of variables, extra variables to be dealt with. So, we will consider, I mean we stop our discussion of rectangular elements here. In our next lecture we will consider practical solution of solving a stress analysis problem by using finite elements, a complete step by step process that will explain the entire process of finite element analysis. Thank you.